An alternative to this, which would greatly improve scalability of the overall system, is for the data center border routers in other data centers not to advertise individual EVPN routes they received from other data center border routers, but just to advertise a single MAC default route. So that's pretty much how we're going to deal with this layer 2 extension problem. Now let's talk about optimizing routing. And as I said before, optimizing routing could be split into two parts: optimizing VM's outbound traffic and optimizing VM's inbound traffic. So let's first look at optimizing VM's outbound traffic, default gateway. The problem here actually is very simple. As VM moves from one server to another, VM is going to retain both MAC and IP address of its default gateway. Now, as VM moves to a new site, MESs connected to that site should be able to apply IP forwarding to all the inter-subnet traffic originated by VMs in that site. And to accomplish this, all what MESs should be able to do, they should be able to trap traffic that goes to other subnet, and they then apply IP forwarding to this traffic. So the question to ask is, how would MESs identify this traffic, traffic that goes to other subnets? Well, it's actually very simple, because this traffic carries in its outside header destination MAC address of VM's default gateway. So there are two solutions to this. One which relies on using what amounts to anycast IP and MAC addresses, where all the default gateways are provisioned with the same IP and MAC addresses. And in this case, MES will just trap these packets because it knows about this default gateway IP and MAC address. And the second approach doesn't require any cast IP and MAC addresses for default gateways, but it uses EVPN procedures to mark specific IP and MAC addresses as addresses associated with default gateway, and you exchange this information among all the MESs. And so as a result, every MES that connects to a given EVPN knows about MAC addresses of the default gateways for that EVPN, and this way it can trap all the packets that go to other subnets. Now let me say a few words about optimal routing, and let me start with intra-data center scenario. The assumption here is that, first of all, top-of-racks switches perform MES functionality, and moreover, in addition to MAC-based forwarding, they also can perform IP-based forwarding. So a solution for optimal intra-data center routing relies on EVPN. And the way how it's implemented is fairly straightforward. As you know, in 2547, you could construct extranets by just manipulating import and export route targets. We do exactly the same here, and that is within a single data center, we could redistribute EVPN routes between EVPNs associated with different closed user groups by just manipulating route targets. And that's how effectively we create host routes to VMs within a single data center. So when a given MES imports an EVPN route into its EVI, it could determine whether this route is associated with VM that is on its own subnet or on a different subnet. If it's on its own subnet, then the MES creates MAC-based forwarding state. And if it's on a different subnet, MES creates IP-based forwarding state. And that's pretty much how you optimize routing among VMs in a single data center. But we also have to cover a scenario where VM communicates with peers that are in other data centers, or just communicates with hosts that are on a client side. And now we're going to talk about avoiding triangular routing for inter-data center scenario, solutions to that. There are two solutions, one which is based on propagating host routes, and the second which is based on next hop resolution protocol. What I want to point out is that both of the solutions could be used at the same time. They're kind of complementary to each other. And both of the solutions rely on the fact that in EVPN, you could advertise, you can propagate not just MAC addresses, but IP addresses as well. So let's start with the first solution. Well, The first solution, we can talk about just propagating host routes as individual IP routes. And that is suitable in an environment where you have a single routing addressing realm, something like data centers or a single enterprise. This approach is clearly not suitable for multi-tenant environment. It is not suitable when a service provider wants to offer cloud computing as a service. And the idea here actually is very simple. All you do effectively is you redistribute routing information from EVPN into plain IP routing. That is, data center border router learns about virtual machines present in its own data center, learns about their IP addresses using EVPN procedures, and then just originate host routes into either OSPF or ISIS or BGP. Important to keep in mind that as data center and border routers will receive these routes, they could avoid triangular routing, yet at the same time, data center border routers in other data centers don't have to inject these routes inside their own data centers. All they have to do is to inject a single default. To scale the system, it's very important to constrain propagation of these host routes. And in the case of OSPF or ISIS, you could use areas as natural boundaries to constrain the propagation scope. In the case of BGP, you could use route targets to constrain the propagation scope. Now, granted that by constraining propagation scope, we also limit the scope of entities that could benefit from avoiding triangular routing. And so outside of the scope, you may still end up with triangular routing. Well, it's not a perfect solution. Another variation on propagation of host routes is much more suitable in what is known as VPN-oriented data centers. For the scenario where you have service provider that offers cloud computing services. And the main difference between this approach and the previous one is that in this case, instead of propagating IP host routes, you're propagating VPN IP host routes. And in data center border router, you have both EVPN and 2547 functionality present on the same box. So you create a VRF on the data center border router. This VRF is populated from two sources. One source is the IP addresses of VMs present in its own data center, and data center border router learns about it using EVPN procedures. And another source is 2547. That's how you learn about IP addresses present in other places. Now let me describe to you yet another fundamentally different approach for eliminating triangular routing, for avoiding triangular routing, which is based on Next Hop Resolution Protocol. Well, I don't know how many of you are familiar with this. It's a fairly old technology. So let me just give you a very short overview of this protocol. As I said, it's a very old technology, circa 1998. It's a standard, ITF standard technology. It's been implemented by multiple vendors. Its original application aimed at eliminating extra hops in the presence of either ATM or frame relay network, what is known as NBMA, non-broadcast multiple access. And so in that particular context, NHRP provided mapping between an IP address and NBMA address. What's important about NHRP is that it provided on-demand mapping. So the paradigm here is you acquire information on demand. Well, later on, people figure out that actually there is no reason to limit NHRP to just ATM and frame relay. And in fact, you could think about NBMA as an IP network too. And in this case, you could just apply NHRP to resolve IP hop into IP next hop. And there's an example of this technology I could want to mention here is Cisco Dynamic Multipoint VPN, which utilizes NHRP precisely for that purpose. Now, in the context of this presentation, when I'll talk about NHRP, I'll be talking about mapping IP address of a virtual machine. And when I talk about NBMA address, I'll be talking about IP address of a data center border router that contains the server that hosts this virtual machine. So we're going to use NHRP to resolve IP address of virtual machine into an IP address of a data center border router that contains this virtual machine. There are all sorts of NHRP messages. We wouldn't need all of them. We need only a small subset for the purpose of VM mobility. There is a concept of NHRP client and NHRP server. So the client originates requests, receives replies, and server does exactly the opposite. It receives requests, and in response originates replies. So let me just outline how an NHRP solution will be applicable to avoid triangular routing. Well, to begin with, a data center border router is going to advertise inter-IP routing system, prefix routes for the IP subnet of VMs that are in the data center, in this DCBR's own data center. Keep in mind, though, that here we're not talking about individual host routes. We're talking about routes to subnets. So they don't introduce, these routes don't introduce any additional overhead to the routing system. That's important to keep in mind. Now, in addition to that, remember there is a concept of an NHRP server, next hop resolution server, and there is a concept of authoritative NH servers. So data center border router is going to act as an authoritative server, but only for VMs that are in that data center border router's own data center. So as a result of it, as VM moves from server in one data center to a server in another data center, its authoritative next hop server is going to change as well. Now, in terms of who can act as an HRP client, it could be either data center border router, or it could be a border router in a client side. What is important to keep in mind when we talk about an HRP is that nobody else besides data center border routers and probably client-side border router has to support an HRP, has to be aware of this. The rest is transparent. So to illustrate you, here's an example of how an HRP will operate to avoid triangular routing. Let's say that in this picture you have a host in the client side and it wants to send a packet to a virtual machine A. So it sends a packet arrives at the client-side border router. At this point, what will happen is that client-side border router will determine that actually this packet falls into the range of addresses that should be resolved using next hop resolution protocol, using NHRP. And as a result, it's going to originate an NHRP message. And an NHRP message is going to be destined to the address of VM. Well, in this slide, what I've done is that I made a data center border router in data center 1 to advertise a route to the whole prefix to 10.1.1.24, which means that an HRP request is going to end up on that data center border router by just relying on plain IP routing procedures. Well, meantime, you should ask me, what's going to happen with that packet? What would border routing client side do with this packet? Well, it'll send it to data center border router 1, because that's what IP routing tells him. Well, once the packet gets to data center border router 1, then DCBR1, relying on EVPN procedures, will send it to DCBR2, which in turn is going to send it to VMA. So meantime, as you see, as you are in the process of optimizing your routing using HRP, you have no losses of traffic. Traffic's still flowing, granted over suboptimal path, but it still gets to its ultimate destination. Well, as DCBR1 receives an HRP request, it'll realize that it's not authoritative for that particular address, but it'll also realize that it's DCBR2 that is authoritative for VMA. So all it'll do, it'll just send an HRP request further down to DCBR2. And of course, what DCBR2 is going to do, it says, well, yes, I am authoritative for VMA. It's in my own data center. So let me send back a reply with my own address as the next hop. Well, once you do that, and once the client-side border router receives the reply, it creates a forwarding state entry. And at this point, triangular routing is eliminated. Well, now let's look at the scenario where VM moves from one data center to another. And we're going to use as initial situation what we reached at the end of the previous slide. So now VM moves from a server in data center 2 to a server in data center 3. Well, what will happen is that at this point, DCBR in data center 2 will notice, using EVPN procedures, that VM moved to a different data center. So what it's going to do, it's going to send a purge message back to the client-side border router. Well, client-side border router will receive this purge message and will wipe out the fib entry that it created before. And from that point on, you're back to the previous slide. You pretty much repeat all the steps that happened on the previous slide. And in the end, you'll eliminate triangular routing and go directly from client-side to the data center border router 3. So to summarize, what I want to do now is to look at the whole landscape, look at the problems we need to solve, look at the solutions to these problems. The first thing we need to address is how to provide intra-subnet connectivity in the presence of VM mobility, intra-CAG connectivity in the presence of VM mobility. The solution for this problem is EVPN. Well, but as I said, we don't want to limit ourselves to just individual islands, individual subnets. VMs on different subnets should be able to talk to each other too. So for this, we need to address the problem of inter-subnet, inter-CAG connectivity in the presence of VM mobility. This problem itself could be decomposed into two parts. First of all, you can talk about inter-subnet connectivity when VMs are in the same data center. And in this case, solution to this, again, relies on EVPN. And what's important to stress out is that EVPN would support scenario when you have either single routing addressing realm or multiple routing addressing realms. In other words, it's suitable both in a scenario where you have data centers owned by the enterprise, as well as data centers that belong to cloud computing service provider. But of course, VMs could be also in a different data centers, or you may also want to optimize routing between VM and its peers in the client side. Well, this problem could be further decomposed into optimizing VM's outbound traffic, and that would again be solved by using EVPN procedures, and optimizing VM's inbound traffic. Well, when we want to optimize VM inbound traffic, you could rely on two different paradigms. One paradigm known as the push model, where you push host routes. And for that, you have two choices. If you have single routing addressing realm, you could just redistribute EVPN routes into OSPF, ISIS, or BGP. And if you have multiple routing addressing realms, like the scenario where you have cloud computing service providers, then you push EVPN routes into 2547 VPNs. But in addition to this, the toolkit I'm describing to you also supports the pool model, where you on-demand acquire routing information. And for that, you use combination of EVPN and NHRP. So what's the bottom line? What's the punchline? The punchline actually is very simple. IETF already has either an existing technologies that are IETF standards, like 2547 VPNs, like NHRP, like OSPF, ISIS, and BGP, or technology that is on the IETF standards track, namely EVPN. You have all the pieces of the puzzle. All you have to do is just to arrange them in a particular way, and that would allow us to provide a fairly flexible way to support VM mobility in a variety of deployment scenarios. And that is the end of my presentation. Thank you. There are a couple of internet drafts which I would strongly recommend you to use. One which describe, the first one which describe EVPNs, and that's a product of L2 VPN working group now. And the second pretty much describes what I presented in these slides. And I don't know if I have time for questions.
Yeah, I think we're a bit out of time. I think Yakov will be around all day. If you want to ask him some questions, he'll be around, especially during the break now, which we have to cut to before the conference folks shoot me for running over. But thank you, Yakov. So we're going take a break now. We're going to take a short 5-minute break now. There's coffee and tea outside. And if you could all get your coffee and tea and jump back in, I'd appreciate it. Thank you.